So part of the notes today is to introduce that vocabulary that we have to be able to use. Again, this is something that we are going to be using a fair amount through the course of classes coming up. First term was something that was on page 2 of that packet last time. It's called an intramolecular force. And again, I'm trying to emphasize it because the next term is very similar to it. An intramolecular force is basically a fancy word for what bond type is it. So this is what holds atoms, individual atoms together within a molecule or a compound. If you break an intramolecular force, if you break a bond, you have changed the identity of that substance. It's called a chemical change. And what I can tell you is in this unit, both these next couple of days with me and then second semester, we are not dealing with chemical changes yet. We are not dealing with changing the identity of something in a chemical reaction. That's going to be the majority of second semester, but not early on. And a quick reminder, when we talk about bond types, we talk about ionic bonds. Like sodium chloride is a great example of an ionic bond. Polar covalent. Water is the representation of a polar covalent. Nonpolar covalent. Remember our diatomics like fluorine, F2, hydrogen, H2, oxygen, O2, so on and so forth. Now there are other things that are diatomic or nonpolar that aren't diatomic, but those are the best examples. The one thing I did not include on this first slide, because this first slide is done then, is metallic bonding. Metallic bonding is a little bit different than ionic and polar and nonpolar covalent, in that it's just a whole bunch of metals all attracted to each other. So we are going to limit our discussion on metallic bonding today when we're talking about these forces of attraction. Metals are held together very tight. You'll see a demonstration of that in a little bit as well. So again, slide number 1, these are the bond types. And what's important, not only for your ability to do the quiz or the unit or sort of semester exam well, but your understanding of chemistry is if we can identify the bond type of a molecule, we then should have an idea of how well it's held together to other molecules. And if we know that, we know which things are more likely to be a solid versus a liquid versus a gas at any given temperature. And that truly is the goal of these next 2 class periods. Last class period we meant to introduce it to you a little bit, but quite frankly, we didn't get very far. Notice this second slide starts off with intermolecular force. This is what holds 2 molecules together. So an intra is the bonding that holds atoms together. Your polar covalent bonds, your nonpolar covalent bonds, your ionic bonds. An intermolecular force is what's holding 2 molecules together. These are the dashed lines I have drawn up on the whiteboard. You did this as well with water for the model activity. General rule of thumb, intermolecular forces are not as strong as intramolecular forces. One of the things I'm going to do is I'm going to flip back and forth between my PowerPoint and Smart Notebook so I can draw a little bit of this on the smartboard for you. So once you get this drawn out, I want to draw the example of sodium chloride. Okay, and we'll come back to that slide. Here's one NaCl. But salt is a whole ton of these little NaCl's attached to each other. So how does one NaCl attach to another? I'll draw a second NaCl in a different color. I'll draw another NaCl in a different color still. I'll draw one more. The exact same full charge that's holding one Na plus to one Cl minus is what's holding one NaCl to a second NaCl, or a third. I mean, it's completely surrounded by it. So ionic compounds are held together really well. And things that are held together really well are usually going to be in a solid structure. I'd like to think that I can manage a classroom halfway decent, so I can have you guys sitting in this solid structure right now in your seats in a very organized manner, and it doesn't take a lot of energy on my part to keep you this way. I would also like to think there are some teachers, maybe they're brand new teachers, maybe they're people who aren't even teachers, that could not get you to sit this way. That if there was just some random person up here, somebody like, whatever, and you're just going to start rolling around the room. Some people might just leave the room because they can't hold them together even well. So ionic compounds hold things together really well. Full charges. So we usually don't talk about them in terms of intermolecular forces, because the same attraction, again, that's holding this Na to this Cl is holding this sodium chloride to this one and that one. If you break an intermolecular force, a physical change has occurred. A physical change just means you have changed something about it, but it's still the same thing. So changing it from solid to liquid, it's still the same compound. A group over there was talking about how you call it ice, but isn't it just water as a solid? Yeah, it is. It's H2O, whether or not it's a solid or a liquid or a gas, it's H2O. I mean, think about yourself. You get a haircut, you have physically changed yourself, but you are still the same person. My very last point on this slide. And this is something that we very commonly assess students on. The intramolecular force. So what holds the atoms together in one molecule determines the intermolecular force. What holds one molecule to another molecule. What I'm going to do then is I'm going to go over the three intermolecular forces that was on your bond type packet, which was on your homework. And hopefully we see this enough and in a lot of different ways, it's going to hit home. Sorry, that's a little for extent. You all ready? Okay. The first intermolecular force, our textbook calls it dipole interactions. A lot of textbooks call it dipole-dipole. Like if you just called it dipole, I would accept that. So I don't want to get too bogged down in the term, because different texts over different times give it slightly different terms. Notice my first definition of dipole-dipole, or just dipole interactions. It's between polar molecules. And this goes right back to the very last thing you wrote down. The bond type determines the intermolecular force. Because polar molecules have partial charges. And if you have a partial charge, you can attract another thing with that opposite charge. Opposites attract is something that we've been talking about since the atom unit. Remember I showed you the little glass tube with a beam and I put a magnet up to it and bent the beam, and hey, that's how J.J. Thomson discovered the electron? This very simple principle of physics guides a lot of what we understand. The last thing I'm going to do for dipole-dipole is I'm going to draw an example of this. And actually, it's going to be the exact same example I have up on the whiteboard here. But that way you have it in your notes as well. Hydrogen chloride is a polar covalent molecule. I know this because chlorine is more electronegative than hydrogen. Trends in the periodic table that we covered earlier in the year. A second hydrogen chloride would then be attracted to it. And we typically show a dashed line to show an intermolecular force. It's not as strong as a polar covalent bond, the line between 1H and Cl. But if we're talking about states of matter, gases are not held together, solids are held together really well, liquids are still held together but not as structured. But we have to go over in this class is how are things held together. I showed you before NaCl, Na plus, the Cl minus, held together really tight by full charges. HCl, what holds one HCl to a second? The attraction between partial charges. So again, you could call that dipole interactions like our textbook does. You can call it dipole-dipole. Usually once you say the word dipole, we know what you're talking about though. Okay, I'm going to erase this. Hydrogen bonding is our second type of intermolecular force. Hydrogen bonding is a special type of dipole-dipole. It's an extra strong one. That's why it has its own category. So once again, it is polar molecules because they have dipoles. But the key with hydrogen bonding is it is stronger than dipole-dipole. It's almost in between a dipole interaction and an ionic bond. An ionic bond is full charges of attraction, and dipole interactions are partial. Hydrogen bond is kind of in between the two. And again, the best example by far, which I already have up on the whiteboard, but I'm going to draw here as well, is water. Water is a polar covalent molecule. I know this because oxygen is more electronegative than hydrogen. That means when you have waters around each other, just like you drew out hopefully a little while ago, the partial negative end of one water is attracted to the partial positive of a neighboring water. That's what holds it together. That's what in freshman biology you did. Water is a sticky molecule. You remember that at all? It looked like little mini mouse ears that you kind of put next to each other over and over again. Again, they try to use that to help explain things like the cellular membrane and flow of water in and out of a cell. But without understanding electronegativity of oxygen having a greater pull on these electrons, that's why it's partial negative, you didn't have the full story until probably now. But water's held together by that attraction. You saw that with the models that you were looking at just a little while ago. Okay? Our last type of intermolecular force is the one that's a little more unusual. Our textbook calls it dispersion forces, but old textbooks called it London dispersion forces. It's another thing where a lot of people just call it dispersion forces, and I'm happy with that. This is far and away the weakest intermolecular force. Every type of molecule will have dispersion forces occurring. It's just that for some of them, it's such a small thing that it doesn't matter. So it only really matters for nonpolar molecules. So again, what I have for my second bullet point is, what is a dispersion force? It's a temporary dipole. And this definition is on page 2 of your 4-bond type packet. So there's still going to be opposite charges attracting each other. But those opposite charges do not last. And just like early on, when I said you should be able to connect bond type to intermolecular force, dispersion forces are what hold nonpolar covalent molecules together. And this is a weak thing. The last thing for text on this slide before I draw an example, the bigger you are for nonpolar, the more of these temporary dipoles you can have. So once you jot this down, I'm going to again go back to the Smart Notebook and draw an example of carbon dioxide. Okay. Carbon dioxide is a nonpolar covalent molecule. If it's nonpolar, that means it does not have partial charges. I'm going to draw a second carbon dioxide right now as well. So unlike the other pictures I've drawn, where there's just naturally a positive and a negative that can attract one another, it's more difficult for carbon dioxide. However, when I draw these dots around the oxygen, those electrons aren't stationary. They're not stuck in one place. They're moving around. So let's say at one particular instance, that set of electrons moves up. That also makes this oxygen a little bit partial positive. Then let's say these electrons, due to random motion, all of a sudden come up a little bit on the neighboring one. That makes this oxygen now a little bit partial negative. It creates a temporary dipole, a region that is for a little bit partial positive and a little bit partial negative. But now we have opposite charges. That's our London dispersion force. The problem with it is it breaks quick, because if that attraction was due to electrons moving around, well, they're going to keep moving around. Larger nonpolars can have this happen a lot. So that's the good news with nonpolars. If they're big, they can have these temporary dipoles all over the place, and enough of them can actually hold you together halfway decent. But London dispersion force, what to remember? Nonpolar molecules. So that's what it happens for. And within those nonpolar molecules, then, they have this movement of electrons that gives you these dipoles for a split second. Okay, so now we can kind of tie all this together. State of matter is a battle between two things. The intermolecular forces, so how well things are attracted to each other, and the amount of kinetic energy. If things are moving fast, it's not easy to hold them together. Okay, think about my example of you guys sitting there on your desk as a solid state. If you were moving faster, it'd be hard for you to stay still. If you are just kind of constantly jiggling around and wanting to get up, get back down, it'd be hard to hold you in place. But if you have a really strong intermolecular force, things can be held together, even if they are moving fast. My last point on this slide, it's very common that we will ask students, bless you, what the state of matter of things are and how that relates to their bond type. So my last slide, at room temperature, we right now have things that are solid, liquid, and gas. Jean is sitting on a solid desk. She has liquid water in her water bottle. She is breathing in gaseous air. It's all at the same temperature. So the amount of motion of the particles is similar. However, what holds them together is different. Ionic compounds, and this is true for metals as well, ionic and metals are solids at room temperature because they have full charges of attraction holding them together. Polar covalent molecules, like water, are typically a liquid at room temperature because they have partial charges holding them together. That's not strong enough to keep them in a rigid, solid structure, but it can still hold them together with this amount of heat in this room. Nonpolar things are typically a gas at room temperature because nonpolar things have those very temporary and weak dispersion forces. Again, the gases that you breathe in, nitrogen, which is N2, well, that's a diatomic. O2, that's a diatomic. Those are both nonpolar. What do you breathe out? Well, you breathe out the nitrogen and carbon dioxide. Just showed you how carbon dioxide is nonpolar. I don't think you have to write down my very last slide. My last slide is just one more way to think about this attraction. So again, I'll wait until everyone's done with this slide, and then I'm going to talk you through the last slide. But I'm hoping that through the course of this, we now know the three intermolecular forces that we have to know in this class. Dipole-dipole, or just dipole interactions. Hydrogen bonding, and then dispersion forces or London dispersion forces. And we get this idea of the amount of attraction will hold things together tighter if it's a big attraction like ionics and metallic things have. And if it's very little attraction like nonpolar covalent things have, it won't be held together very well. Okay, so again, the last slide, I don't think you have to actually write down. That's kind of why I put it in italics. I want to give you another example of how things are held together. I like to think of dipole-dipole and hydrogen bonding like a rope holding two things together. So if we were to clear all the desks out of the area, and I grab one end of the rope and Tess grabs the other end of the rope, we are now two things that are held together. If we are walking around slowly, if I go this way and Tess goes the other way, one of us is going to feel a tug. And then, okay, I can follow you, not a problem. I mean, I can do it with my eyes closed. If we're moving around slowly, eyes closed, Tess goes one way, I go the other, I feel her tug, okay, I'm going to go with Tess. Oh, I feel her tug, okay, I'm going to go with Tess. But all of a sudden now, what if we speed things up? What if instead of walking slowly, we walk fast? It's going to be a little bit harder to hold on and tug and go in the other direction. What if we start running? One of us is probably going to let go of that rope at some point because if we're running in opposite directions, that connection that's holding the two of us together will break. But if we're moving slow enough, a dipole-dipole and a hydrogen bond, it's pretty good at holding us together. London dispersion force is like a piece of thread. So if I grabbed one end of a piece of thread and Tess grabbed the other, boy, we'd have to be going very slow, probably eyes open looking at each other, So that thread wouldn't slip out of one of our hands and break that intermolecular force that's holding the two of us together. I do mention, however, that if we had like 1,000 threads, like a large molecule can have a lot of dispersion forces, enough threads almost makes a rope. So I bring this up as another way to visualize state of matter is two parts. How fast things are moving, but how well they're held together.